Hello folks, and how are you all doing? So in the last video we created one cellular automaton called Conway's Game of Life. Now in this video we will be building one slight variation of that called Brian's Brain. So in the Conway's Game of Life we had two kinds of cells, either a living cell or a dead cell. And there were some rules to transition from a living cell to a dead cell, or even a dead cell how it becomes a living cell. Now similarly in the Brian's Brain there are some rules, mostly similar rules, but the key difference is we are adding one additional state, and that is the dying state. So living cells don't die directly, it goes through another state called dying, and then it dies. So living cells are once again represented by white colors, and dead cells are black, and the dying cells are grayish. And this gives quite a very interesting behavior. So as you can see, there are lots of very interesting particle formations or organisms, whatever you might call. So there are these lines moving. There are also some rocket kind of things, as you can see. So these things look like some kind of rockets. This one you can see here, or this one. And there are also a lot of interesting particle formations forming. So we will build this thing using very simple rules once again. So regarding the rules, there's not much change. So when we have two or three particles nearby, a dead cell may become alive. But when we have a dying cell, it will first become dead, and only then it may become alive once again. So dying cells generally die. They don't have anything else with them. And for living and dead cells, the rules are mostly similar. So let's go back to our VS Code and let's build a Brian's brain. So in our VS Code, we have once again a very self-explanatory index.html file. We have a canvas, we have two buttons, next turn and start, and it is connected to a script.js file. And there we have some rules. So the rules for Brian's brain is very simple. So we have living cells, dying cells, and dead cells. So all the living cells in the next turn will become a dying cell. There are no exceptions. And whenever we have a dying cell, it will become a dead cell. Once again, there are no exceptions. And lastly, when we have a dead cell, that is all the black boxes. And when a dead cell has two living neighbors, it will become a living cell. And then it will repeat. And with these very simple rules, we can create a Brian's brain. Now we will start by creating our canvas and context, and then defining all the variables and as it is. Now we have done all of these things in our Convex game of life. So I would like to copy paste rather than write all of these things once again. So we will need our canvas, then our context. We have a width and height, and then we have some dimensions like grid height, grid rows, and grid columns. And then we will also define our next turn and start, the buttons that we have defined in our index.html file. We will define a grid and the next grid, and then we will start by initializing our grid and drawing our grid. So let me copy all of these lines and paste in our script.js file. Now, if you wish to write all of these things from scratch, and if you want a tutorial, you can just visit my last tutorial on Convex Game of Life, and we have done all of these things from scratch. Now, if I go to my browser, and this is how our canvas looks like right now. I will open the inspect and console. There is nothing at the moment because we have not done anything. So what we need to do now is we have to initialize our grid. We have defined everything. Now initialization means we have to give all the values. So our grid right now has, if we calculate, and the grid side is 20, and there are 25 rows and 25 columns, so it's 25 cross 25. So 625 boxes we have. We cannot see right now, but we have, and we have to give a value to all of these boxes. And after giving the values, we also have to draw. So if we have a 1, we will draw in white, and for the grays, we can give a value of zero point 0.5, and otherwise, we will give the value of 0. So we will take this function initialize grid, and if we look carefully what this function is doing, this function is looping through the grid, and it is giving the value of 1 if our random value is more than 0.7, and 0 if it is less than that. Now this is for two values in our convex game of life. Here we have three values. So let me also do one more thing. If the value is, let's say, greater than 0.5, um, we will give the value of 0.5, otherwise we will give the value of 0. And then we also have to draw whatever we have. So we will take the draw grid function, and let me copy it here. And what is the draw grid function doing? It is once again looping through everything, and then it is first of all taking the stroke style as white. This will draw our borders. Now, if we have a white, if the grid ij is 1, we have a fill style of white. Otherwise, we have a fill style of black. Here we also have to add a fill style of gray when the value is 0.5. So I will simply add if grid ij equals to 0.5. In that case, let me copy these two lines once again. This and this. And the fill style in this case will be gray. If we go to our browser, we still have no changes because we haven't called these functions. So here we will do an initialize grid, and then we will also do a draw grid. And now we have something like this. So all the white cells you see, these are living cells, and the gray cells are our dying cells, and the remaining are the black cells, which are our dead cells. Now we can add some more pixels. Believe that's not an issue. So we have 10. Okay, we have 20, we'll make it 10. So we will have a 50 cross 50 grid, and this is what it is. So now the next things that we have to do is whenever we are clicking on next turn, we want the, the grid to change according to the rules. So how can we do that? So what are the things that we need to do next? So we have a button called next turn. So whenever we are clicking on the next turn, we have to do something. So next turn dot add event listener dot click. In this case, we want to do a few things. So first things first, we have to update our grid, and then we again will draw our grid. Now we have to create the update grid function, and this is also a function that we have created in our Conway scheme of life, and this is the update grid. So there will be a little bit of changes here, but the overall structure of the function will remain the same. So I will just copy this one. And so what the update grid function is doing, um, right now, if I press on next turn, we are getting an error, and that is neighbor count is not defined. That is because in our update grid function, so first of all, it is initializing our next grid. So next grid is the same as our grid right now. Then we have a for loop for our rows and columns. And then we have two rules, how living cells die and how reproduction happens. There will be some changes here. But whenever we are trying to calculate these things, we are calling another function, and that is a neighbor count. So whenever we have a cell, we will have a neighbor count. So how many living cells are there and whatever. And this neighbor count function is not defined, and that is why we were getting the error. So let me just create a function called neighbor count so that we at least don't get the errors. Now, if I click on next turn, nothing will happen because the neighbor count function doesn't work. Um, but before going there, let's assume that the neighbor count function correctly counts the neighbors. So what do we need to do next? So we need to change this part. We don't need this part, um, simply because the rules are different. So for our Brian's brain, we have three cases, one for the dying cells, another for the dead cells, die or dead cells, whatever, and lastly for the reproduction. Now, when we will have a dying cell? Whenever there is a living cell, we will have a dying cell. It's very simple. There are no exceptions. So first of all, we will have neighbors equals to neighbor count, and neighbor count from where? From the index ij. The index ij is something that we are iterating over here. Now, how to get the dying cells? So we will check if grid ij is living cell or not. And living cell means the value is 1. If this is the case, then in the next grid ij, it will become a dying cell, so the value will become 0.5. Now for the dead cells, it's actually die rather than dead because they are not yet dead. So grid ij. Whenever we have a dying cell, it will become a dead cell according to the rules. So if the value is 0.5, the value in the next turn will become 0. So grid ij will be equals to 0. Now lastly for the reproduction. Now this is little bit tricky, not much, only little bit. So first of all, we have to check if we have a dead cell or not. Only then it can become a living cell. So first of all, this should be equals to 0. And then we have to check the neighbor count. So if our neighbors equals to 2 only, so only for 2 living cells, it will become a living cell. So next grid, ij, in this case will become 1. So, and lastly, we will map the next grid onto our grid. So this is what we are doing. And if we compare with our rules, this is the same. So the rules are updated for our Brian sprint. Now we need to write our neighbor count function. Now this function will be little bit tricky for our Brian sprint. Now if we check in our convex game of life, what we were doing. So we have an ij index and we were initializing a count to be 0. Now, whenever we have a box or we have a cell, let's say this cell, it has a top row, 3 boxes at the top, 2 in the middle, and 3 in the bottom, apart from the current one. And this is not a round world, which means whenever we are going at the corners, um, there is nothing else on the other side of the corner. So in that case, it is not a round world for the convex game of life. But there will be some issues if we don't apply a round world in our Brian's brain. Now we'll see what it is. So what we are doing here. So we are checking um, if the value of I is not equals to 0 and j is not equals to 0 for the top row, then we are basically adding the count and we are taking the I minus 1 and j minus 1. This is the top left. Then this is the top middle. So I minus 1 and j. And lastly, this is the top right. So I minus 1 and j plus 1. Now, why we are checking these things to be not equals to 0? And here this should not be grid rows minus 1. So why these checks are there? This is because if we have the top row, and let's say we have this box over here. So this is 0, 0. And both I minus 1 and j minus 1 will be minus 1, which is an invalid box. And so it is essential that we are checking this. So what it means is if we have this box in the corner, we will only check 3 boxes. We will not check the other boxes. And similarly, in the top right corner, if this is the box we are checking, um, so the value of j will become minus 1 and the value of I may become more than how many columns are there. So because of these reasons, these are some essential checks. And this is for the top row, same for the middle row, and same for the bottom row. Now, first things first, we will copy this function. But this function is not sufficient for Brian's brain. We will see why. So this is what we have now. Now, if we go to our browser and do an extern, as you can see, our boxes are changing. Now, there is a slight issue. We have a lot of dying cells, and the cells are not dying. The reason being, here there is an issue. So, in our convex game of life, the variables were only 1 and 0. So, we could sim directly add a count. So we were checking how many living cells are nearby. So we are just adding plus. So either it is 0 or 1. If it is 0, it doesn't matter. But if it is 1, it matters. But in the Brian's brain, we also have a zero point 0.5. So in a lot of the cases, a lot of 0.5s are being added and which is causing an issue. So how to resolve this issue? It's very simple. We have to add a maths.floor so that all the 0.5s will become zeros. So this is something that we will add for all our lines. So maths.floor. So here also. Then in our grid for the middle rows, and we have three more to go for our bottom row. Now the behavior will be slightly better, but still not that good. So as we can see, it is still behaving a little bit strangely. Um, okay, so let's try to understand why we are not able to get rid of the dying cells. So what we are doing here. So if the grid ij is 1, it is becoming a dying cell. And here is the issue. Here we should be adding this in the next grid, not the grid directly. And that is why we were not able to get anything. But yeah, still there will be some issues. So we have dying cells. And as you can see, it is working, but we will see whenever it is approaching the end of the screen, it will disappear strangely. And this is the reason we have to apply a roundward. So here you can see a glider has formed already, and it will run like a snake in a diagonal path, but it will also not survive when it approaches the wall of death, you can say. So now it's about to die. And yeah, so this is not good. We have to apply roundward. But before doing that, we can at least automate this one. So what we will do here is, um, whenever we are clicking on the start, so add event listener flick in this case, we will automate this part. So set interval. Let's give the value to be 100, and we will do an update grid, and then we will do a draw grid. Now let's see. Also, let's make it 100 cross 100 rather than 50 cross 50. So I'll give the grid size to be 5. Now, start. So we already have a very interesting behavior. Now the only issue is whenever these things are approaching our walls, it will die. And this is something that we need to take care of. And we'll see how we can do this thing. But yeah, we already have some sort of an interesting behavior, and the glider will die. One more thing we can do is we don't really need the strokes. So here, in our draw grid, we don't need the strokes. So we will comment out these two lines. Actually, we don't need all of these lines. Mm, we don't need these things. We can comment or we can also delete. Really doesn't matter. Because I feel the white lines are a nuisance, and this looks much, much better. And also we can do one more thing. Um, if we are giving white, gray, and black, instead of that, what we can do is we can give it blue, and instead of gray, we can give a light blue. I think this will also look very interesting. Start. Hmm, not half bad. What do you say? Um, so you can check it out yourself. I think we can give an orange. Let me try with some colors. So text color. Okay. Background color, orange, light orange, light salmon. So let me give an orange and a light salmon. So orange, light salmon. Now let's see. Start. I think you can definitely try with the colors. So you can also add more intermediary states. So So this is a dying cell. This dying state is actually an intermediary state, right? So it is in between the living state and the dead cell. So what it does is it transforms the living to the dead. Now you can also add more intermediary states, and you can try it out. For now, for the code, let me just keep it white and gray. But as you can see, we can definitely add more. Now, coming back to our neighbor count and our update, how can we apply the round world? Very simple. Not that simple actually. So whenever we have the corners, we have to compare with the cell over here, right? At the top, we have to compare with the cell at the bottom. So this is something that we need to do to apply our round world. This is a bit tricky. It's not that easy, but yeah, we can do that. So for example, in our neighbor count in the top row, what we are checking, this is for the top left. So even in the top row, this is for the top left. Then this is for the top mid. Then lastly, this is for the top right. Now for the top left, if we see what we need to do, so so if I is not equals to 0 and j is not equals to 0, this is something that we are checking. Now now what about if these things are 0? So what about then? So in that case, there will be three cases. So the first case is, let's say, when the I is equals to 0, but the j is not equals to 0. So what is this case? This case is I is equals to 0 means this is at the leftmost line, but the j is not equals to 0. So it is not at the topmost. It can be any other points. So in that case, we will have a case. There can be another case, so else if I is not equals to 0, so it is not at the leftmost line, but j is equals to not 0, but our j is equals to 0, of course. So which means that the I is not at the leftmost line, but the j is at the topmost line. So this whole line. So any of these boxes, it is taking into account. Now, if such a box is there, we will have another case. And lastly, we will have another case when both are equals to zeros, and that will be part of the else case. Now, in this case, what do we want to do? We want to do a count plus equals to our math.floor. And here, instead of doing an I minus 1, we cannot do an I minus 1. And that is because the I is 0, I minus 1 will become what? It will become minus 1. But what is the meaning of minus 1? So my minus 1 means one box to the left of here. So that means the rightmost box. So that is how we can apply the round world. Um, Let me write over here. Applying round world. Yes. So this will be grid calls minus 1. And for the j, this will become a j minus 1. That is not a problem. And then let me copy this one here. So here the j is equals to 0, but the I is not, so we can have an I minus 1. But for the j, we will have a grid rows minus 1. And lastly, we have an else, and here the count plus equals to will be very simple. And so what does it mean? When both are equals to 0, it means this top left corner point. This is the point we are analyzing. So here it will be very simple. Math dot floor and grid calls minus 1 and grid rows minus 1. Now, this is only for the top left. Now, so we have 8 cases like this, and all of these cases will be huge. Now, I don't want to write it like this because I have already written it, and writing it is very error prone. We can have some errors. So what I will do is I will just copy paste here, and uh, and I will simply explain that what is happening over here. So this is for the mid rows. So if I is not equals to 0, that is the case number 1. And the case number 2 is I equals to 0. So, so we are analyzing the top mid, right? It's not the mid row, this is the top mid. But for simple analysis, let me also increase the size of the box to 25, let's say. Yes. So top mid. So we are analyzing this one. So there are only two cases, I equals to 0 and not equals to 0. Um, yeah. So so whenever equals to 0, we have something to take care of. Otherwise, we have something else. And yeah. So this is top mid. So whenever I equals to 0, we can do an I minus 1 j. And whenever it is not equals to, whenever it is equals to 0, which means this is at the leftmost. And in that case, oh, now one more thing. This I is actually taking care of the rows and j for the columns. So I believe so. I zero means this is the topmost row. Any other I means this is another row. So this is any of these rows. I equals to 0 means the topmost row, and the j can be anything, means it can be any point. So in the topmost row, it can be any point. So that is when the I is equals to 0, and we have to take it as grid calls minus 1, which means the last line. And for the other cases, we can have as it is I minus 1 check. So this is for the top mid. Lastly, for the top right, this is very similar to the top left, and this is what it is. So I is not equals to 0 and j is not equals to grid rows minus 1. This is the case. Um, we will have I minus 1 j plus 1, and the other cases are one I is equals to 0 and j is not equals to grid rows minus 1. Second case is j is equals to grid rows minus 1, I is not equals to 0, and the other case is both are equals to. So what it is checking? It is checking I equals to 0 means, again, it means the topmost row, and j equals to grid rows minus 1 means thus this last line. And so when both are not equals to, we can have j plus 1. Otherwise, j plus 1 will become the right side of this row, which is basically the first row, and which is basically j equals to 0. And that is what we are taking in these two lines. So grid I minus 1 0 and grid calls minus 1 0. So this is how our top left, top mid, and top right is taken care of. And in this case, if we start, what will happen? As you can see, something is coming from the top. Yes. So we have these two. These two are connected. So that's why we are having this. But we have to connect the mid and the bottom. And then this will become complete. So this is not half bad, but we have to connect the whole. Then we will have all the very interesting behaviors. Now for the mid rows, we have two cases. This is the mid left, and then comes the mid right. Mid right. And this is very simple. So for the mid left, we have to apply this. J is not equals to 0, then this. And if j is equals to 0, then this. For the j, it is changing. And for the mid right, we have this. So j plus 1 we can only do when it is not equals to grid rows minus 1, otherwise it will become 0. Something similar to our top right and top left for our j. And lastly, we have what? We have for our bottom rows. And for our bottom rows, once again, we have the bottom left, then the bottom right, and lastly, uh, the previous one was the bottom mid. So this is the bottom right, and then it was the bottom mid. And very similar to the top left, top right, slightly different. Mm. So for the bottom left, this is what we should be having. We should check against grid I should not be equals to grid calls minus 1 and j is not equals to 0. This means we are taking the last row here. And for the j, we are checking these are not equals to 0. Um, and whatever, you can just take a look. And this is actually very simple. And this for the bottom mid, and lastly this for the bottom right. and we have more or less some kind of logic ready. Now, if we do a start, if you can see, both our sides are working fine, which means we have some kind of branch span working. So as you can see, it is some sort of a rocket-like thing, right? So some rocket is going on, and it looks like at the there is some sort of a combustion engine or something like that that is firing at the bottom. Like bottom is bottom of the rocket, and there are a lot more interesting structures that we will generate from the branch span, and we'll see we have to only decrease the size of our grid site. So let me make it 4. So it will be 125 cross 125. And then if we do a start, and let's see the fun. So we have a glider once again. So gliders will, and it's gone. And we have many small rockets, many big rockets. So this looks like a small rocket here, and this is also another kind of rocket with some fuels. And there is a huge rocket, and there are also a lot of structures that will create other structures. And but in the end, generally these things come to a stabilizing point where we have a stable structure. Yes. And lastly, one thing that I would like to mention is we can actually play with more states. So we have a dying cell, we can have more dying cells, and that is how we can basically generate. Here what we are doing is, if we go to our neighbor count, not the neighbor count, if we go to our update grid, so dying. So dying, we are converting 1 to 0.5 and 0.5 to 0. What we can do here is we can convert 1 to 0.7. This is dying. And before dying, we can have another state, almost dying. And here we can convert this to a 0.3, let's say. Mm, And we won't be having this. If it's more than 0.7, it's 1, otherwise it's 0. Mm, I think it's not wise to have so many states. Now, if we do a start, everything will be gone because we don't have the new logic for our new dying, almost dying. So, so 7 to 0.3. So from 1, it will become 7, and if it is 0.7, it will become 0.3. And lastly, if it is 0.3, it will become 0, and then 0 to 1, if it has two neighbors. Now, the neighbor count and everything will be same. Here we need to add another drawing. So else if the grid ij equals to 0.3, so this is 0.7, then we need to add something more. So it will become white to, let's say, light gray to black, something like this. Now if we do a star, so we have rockets and we have 3-layer rockets, you can say. And there is actually a slight issue. The issue is we no longer have such interesting structures. Most of the structure seems to be gone because those are suitable only for 2 states, not 3 states. Um, um, but we can definitely play with colors. So if we do a color wheel, and if we take 3 level of colors, so red, then light red, 2 levels of light red, this one and this one. And if we take this, so if we come here, this will become red. And from the red to a darker red, so let me take this, and then a lighter red, so something like this. Now if we take this and if we come here and start, um, I will leave this up to you to create better colors and better states, but this is the basic idea. This is how we can create this cellular automaton. And yeah, so that's it for this video, folks. In the next video, we'll we'll come up with something more interesting. And see ya next time.